This is a demonstration video of our deep reinforcement learning project.
First, we perform a simple Q-learning for a maze problem, which has been introduced before in class. Since this is a 6x6 matrix, there are 36 states in total. The 4 actions in this problem are left, right, up and down. We set the rewards as follows. If the agent was trapped, it got minus 20 points. The agent can also get 20 points for walking out of the maze. Also, there's a trifle in this maze which is worth 5 points. In this problem, we performed a simple Q-learning instead of deep Q-learning, which is basically an implementation of the Bellman expectation function. For each episode, the actions are chosen based on their current states and trade-off between exploration and exploitation. The Q table is updated where we set the gamma as 0.9 to update the Q value. For this simple problem, the agent could find the best policy within limited rounds.
The second case is trying to let a 2D vehicle learn and find a path in such a map with square obstacle in the mid. The environment model was set the states of the car are given by 5 distance information from sensor attached to it, while the actions are given by directions that the car can proceed. The reward was set up as -1 whenever the car has a collision either with obstacle or the window, while it's 0 for all other situations. This is what the environment looks like. The infinity states model runs a basic deep Q-learning that use value as activation function and a time window capacity of size 2000. The way it updates the Q value is similar to the pseudocode we discussed in the class. In each randomly selected state, a possibility was set to manipulate the process of action selection. As more episodes has been completed, the Q value is considered to be more trustful, while it leads such a possibility of random action selection to be less. The exploration-exploitation process and moving window memory proceed in each step, and then Q function is updated in each episode. Another similar case manipulates a robotic arm that aims to reach an effector to the blue point, while the blue point can be moved with user input. The states of this case can be described as the end effector position with 2 arms rigid body limitation. The actions can be the same as the degree of freedom, 2 actions given by 2 revolute joints. The reward was set linearly based on how far the end effector is from the blue point. The further state will give a more negative reward, while touching or continuous stop generates a positive reward. The learning process is very similar to previous one, but with larger window size and more complicated neural network. This is how the run goes.
Finally, we applied deep reinforcement learning to play catch game. In the catch game, for every fruit being caught, the player gets 1 point, and for every fruit not being caught, the player loses 1 point. There are 3 different actions: move the basket to left, move the basket to right, and do nothing. The goal is to choosing the actions that lead to the highest score. During this gameplay, all the experiences are stored in the replay memory, and in the training, batches of the random drawing experiences are used to generate input and target. Our agent will randomly select its action at first by a certain percentage called exploration rate, where we set as 0.1. This is because at first it is better for the agent to try all kinds of things before it starts to see the patterns. And when it is not deciding the action randomly, the agent will predict the reward value based on the current state and pick the action that will give the highest reward. Since we don't want to store infinite memory, we just delete the old ones. In the gameplay, we built a deep neural network with 100 hidden layers, and the ReLU was chosen as the active function. The results are shown in the code. We found that the model needs about 4,000 runs until it can play good enough.